Well, hello, everyone. This recording is for this week, for Wednesday, November I guess it's the 25th. And purpose of this recording is to give you an introduction to a new topic called hypothesis testing. I'm recording this not only for my statistical literacy classes at Rowan University, but also for my Introduction to Statistics class at Camden County College. Both classes are starting hypothesis tests at the same time, so I thought I'd do this recording for both of you. For statistical literacy, the introduction, I will show you things without formulas. There won't be any formulas because when you actually do these hypothesis tests, you're going to be using StatKey. There's something called a randomization hypothesis test that we're going to do in StatKey, which I will start showing you next week. For Camden County College class, you'll be learning the traditional way of doing hypothesis tests. So you will be learning with formulas. Okay, so that's the distinction between the two classes. But for both of classes, this is a nice introduction. Now, one of the things I will be doing tonight is I'm going to be showing you a video. This comes from a video series on statistics by Professor Williams. This video comes from also, these videos actually come from a company called The Learning Company. And they do a series of courses called the Great Courses. So anyway, this course, in my opinion, is an advanced introduction to statistics course using the R programming language. Obviously, for our statistical literacy course, this is not something that we're going to be pursuing. Even for the Camden County course, this goes a little bit beyond what you guys are doing too. However, Professor Williams does a very nice job in the first 11 minutes and 40 seconds or so of this video, introducing you to the topic of hypothesis testing. So I'm going to let her talk about this with you first, and then I will continue. I've created a PDF document which I will post in Canvas for both schools, both courses, and that will go into just slightly more detail than Professor Williams does, but she does such a nice job in introducing this topic that I thought I would share her introduction with you. All right, so let's do that first. All right, so let me just stop share in a second here. I just have to find her video. There we go. Just give me 1 second here, set up the share screen. There we go. All right. So I will make sure that the computer sound is also shared so you can hear it. All right, and here it goes.
The past few lectures have been about parameter estimation. How do we use our sample data in order to estimate a population parameter, like the mean? So we learned that we can take our sample mean and we can use it as a point estimate of the population mean. And we could even build a confidence interval around that estimate. And so this confidence interval would be where, say, 95% of the time, we would cover the true mean. But there's another way that we can look at our data. Instead of using our data to estimate a population parameter, we could instead guess a value of our population parameter and then ask ourselves, do we think our sample could have come from that particular population parameter? So instead of going from the data to the parameter, we could actually go vice versa. We could go from the parameter to the data. We call this new approach hypothesis testing. Now, we do hypothesis testing practically every day in real life. In fact, every time I go grocery shopping, I'm likely to do a hypothesis test. In fact, here's one time when my hypothesis test didn't quite go so well. Now, my family loves a particular type of almond milk. And, I'm going to the store and I'm shopping for it one day, and it's the sweet vanilla kind. Okay. So I'm in the grocery store and I noticed there's a different brand of almond milk and it's on sale. I mean, it's like a good sale. It was $1 off. And so I'm thinking, okay, it's the sweet vanilla kind. It's just a different brand. It'll probably taste just as good. And it's $1 off. So we're fixing breakfast for our 3 boys the next day, and I take out this new brand of delicious almond milk. No big deal. They're young. What do they know about almond milk anyway? And it was $1 off. Well, to put it nicely, they hated it. I mean, their faces got contorted and nobody finished their cereal. And as you can imagine, I have never bought that brand again. So what was my hypothesis? Right? It was that this brand new almond milk is just as good as the old brand. And what do you think my sample data was? Well, that was my 3 sons' reaction to this new milk. And did my data support the hypothesis? Absolutely not. In fact, my data flat out rejected my hypothesis. So what is a hypothesis? Well, in general, a hypothesis is just an educated guess about something in the world around you. Maybe something that you can be able to test or experiment with or observe. Now, in hypothesis testing, what we really want to know is whether the characteristics of our sample match the underlying characteristics of our assumed population. So with the milk, my assumed population was that, it should be just as good as the old brand, right? The new brand is good as this old brand. But is sampling just 3 people sufficient? Now, at our breakfast table, the samples weren't even independent. Maybe one of them in the 3 were influential over the others. And it's not enough just to do a visual comparison, right? We need a quantitative way to evaluate our sample relative to some baseline. And that's what statistical hypothesis testing is going to do for us. Now, formally, a statistical hypothesis test is a claim about our population parameters. And when we do hypothesis testing, we're going to start with 2 pretty contradictory hypotheses. The first is our null hypothesis. We call that H naught. Now, this is the claim that's initially assumed to be true. It's like our prior belief, our old theory, the status quo, the current standard. And then there's the alternative hypothesis. We call that HA. This is our contradictory claim, the competing claim. Maybe it's the new theory or some alternative standard. And so we need a way to decide between the null hypothesis and the alternative. And this is what our decision principle is. We're going to reject the null hypothesis in favor of the alternative if our sample shows some strong evidence that that null hypothesis is false. Otherwise, we don't reject it. Statisticians also say we failed to reject H naught, like it's a failure if we can't reject the old theory. Now, hypothesis testing uses our sample data to make decisions about the population. We can specify our testing procedure with the following. So first, we're going to need a test statistic. Now, this is going to be some function of our sample data that we're going to use to make a decision, right? Whether or not we reject or fail to reject the null hypothesis. So that decision is going to be based on this test statistic that we calculate from our sample. Secondly, we need a rejection region. So this is going to be the set of all test statistic values for which the null hypothesis would be rejected. And then finally, we need a decision rule, right? So we're going to reject our null hypothesis if our test statistic falls in the rejection region. Now, the null hypothesis is assumed to be true, and we have to provide the statistical evidence needed to reject it, right, in favor of the alternative hypothesis. Now, if you've ever had jury duty or watched a court case on TV, then you've seen hypothesis testing in action. Seriously. So in criminal trials in the United States, the defendant is innocent until proven guilty. So in other words, our initial assumption is that the defendant is innocent. Now, let's see what hypothesis testing looks like for a population mean. In this case, the null hypothesis is that the mean of our sample is equal to the mean of the population. So mu is equal to mu naught. Now, this is assuming that the null hypothesis is true. Now, we often test whether our sample mean is different from 0. So H naught, that mu is equal to 0, would be our null hypothesis. The alternative would be that mu is not equal to 0. Here are a couple of examples of alternative hypotheses. We could test that our alternative is greater than mu naught, the mean under the null hypothesis, that is less than the mean under the null, or that is not equal to the mean under the null. Now, there are two types of errors that come up in hypothesis testing. The first is a type 1 error. In this case, we're going to reject the null hypothesis when it's actually true. Right? We call this a false positive because we think we found something new, but we actually didn't. Another type of error that we make is a type 2 error. This is when we fail to reject the null hypothesis when it's actually false. We call that a false negative, right? Because now we've missed some new result. Now, we have two terms, alpha and beta. Alpha is going to be our probability of making that type 1 error. And beta we call the probability of making a type 2 error. Now, you can imagine we want to keep these as low as possible. But there's a contradiction, right? As soon as we try to balance the probability of making a type 1 error, well, it changes our probability of making a type 2 error, right? So we can decrease the rejection region and get a smaller alpha level, but a smaller alpha level is going to give us a larger beta, right? So our type 1 error, this is usually the one that's more serious to us than the type 2 error. And here's why. All right, let's go back to the criminal trials. We're in the United States. And again, we've assumed that our defendant is innocent until we prove them guilty. So in this case, what's our null hypothesis? Well, that would be that the defendant is not guilty. They're innocent. The alternative is that the defendant is guilty. Now, we always assume the null hypothesis is true unless we've got sufficient evidence, right, beyond a reasonable doubt to reject it. So in hypothesis testing, our data are the evidence, right? If there's enough evidence in our data, we reject the null hypothesis. And if there's not enough, we fail to reject. So in this case, a type 1 error would be like convicting an innocent person, right? The evidence led to a wrong conclusion. And if we made a type 2 error, that would be like setting a guilty person free, right? There's not enough evidence to prove guilt. But because we want a just and fair process, we assume that everyone is innocent, right? Until they're proven guilty beyond a reasonable doubt. And the proof is going to be in that data, this large body of evidence that's going to be presented to suggest whether this person committed a crime or not. Now, if we wanted to say control for the type 2 error, meaning we would never set a guilty person free, we would also end up convicting a lot of innocent people. On the other hand, if we control for the type 1 error and never convict an innocent person, then we end up setting guilty people free as well. So we typically choose the largest alpha that we can tolerate. Let's say alpha equal to 0.05. So what this means is we're willing to mistakenly convict an innocent person 5% of the time in exchange for making the right decision 95% of the time. Now, if we couldn't tolerate that, we could also choose a different level alpha, maybe alpha 0.01. So then we'd mistakenly convict an innocent person 1% of the time, right? And correctly make the decision 99% of the time. We call that alpha our significance level. All right, let's look at the following types of hypotheses. And I want to kind of prep you for where we're going to go with this. 3 ways that we look at hypothesis testing. And first is an upper tail test. So the null hypothesis is that mu equals mu naught, some mean that's assumed under the null, versus the alternative is that our sample comes from a population that has a mean that's greater than the mean under the null. So mu is greater than mu naught. A lower tail test is the opposite of that. Now we're assuming that our sample comes from a mean population that might have a mean that's less than the null. So that's our alternative hypothesis. And then lastly, we can do a two-tailed test. Now we're looking to see if our sample is different from the null, either greater than or less than.
Okay, so I'm going to stop the video right there because she's going to start getting into some technical things that are for formulas. And again, for all of you who are taking my statistical literacy course, we're not going to be doing hypothesis in that way. You probably are saying thank God for that. For Camden County students, you'll be using your formulas, so, but you're already excited about that, I'm sure. All right, so let me now share with you the PDF that I've set up for this. Basically, now that she's described a little bit about hypothesis tests, and hopefully much of that made a great deal of sense to you, I'm going to give you just a little bit more detail on it. So let's get to the PDF that I've set up. All right, so she talked about two types of hypotheses: the null hypothesis, which is basically the hypothesis that is accepted right now. So it's basically what people generally accept. And then we have the alternative hypothesis, which is a competing hypothesis. It challenges the null hypothesis. Now, when we actually write these hypotheses, number one, we have to know that the hypotheses are claims about populations, not about samples, all right? So as she mentioned, we're going to use the sample to test whether a claim about a population, basically the null hypothesis, whether there's enough evidence to reject it or there is not enough evidence to reject it, all right? And when we do reject the null hypothesis, we're going to end up going with the alternative, the competing hypothesis. Now, just for some practicalities, you might have seen this on the video, but I'm going to mention it to you again. And I'll post this, obviously, so you can see it in Canvas. This is the way we write. This is a symbol for our null hypothesis. It's H, and sometimes people call it H naught, naught meaning 0, or H sub 0. But it's a big H with a little 0 down next to it. Okay, so that is the symbol for our null hypothesis. Now, our null hypothesis always has an equal sign in it, right? It doesn't have less than or greater than or not equal to, always the equal sign. So an example would be our null hypothesis, H naught is mu, which is our population mean, is equal to 5. That's one example of a null hypothesis. So this is a case where we have a measurement variable, one that we are measuring something. So we have mu as the population mean that we're testing. If we're looking at proportions, we're going to use the letter P to represent a population proportion. So mu represents a population mean. P represents a population proportion. If we're testing that, it would be P equal to 0.35 as an example of a population proportion that we're testing. Now, the alternative hypothesis, once again, is a research hypothesis that challenges the null hypothesis. And the symbols that we typically use in it will be either greater than, or less than, or not equal to. All right? We never use equal to in the alternative hypothesis. All right, so this is very important to understand that. The symbol that we're going to use is H with a small a next to it. Typically, people pronounce it H sub a, but that's the alternative hypothesis symbol. Now, typically, you put a colon next to it, and then you put the the alternative hypothesis next to it. Now remember, the symbol is either going to be greater than, less than, or not equal to. Dr. Williams was mentioning that right near the end of the video that I showed you in those three cases that she was referring to. But some examples would be, for example, if we were testing a population mean of 5 in the null hypothesis, we could, as a competing hypothesis, either have mu greater than 5 as the competing hypothesis, mu less than 5, or mu not equal to 5. Right now, 5 is just some number I picked. All right, that doesn't mean anything. It's just a particular number. Or, as an example of a population proportion, if the null hypothesis is p is equal to 0.35, then one of these three would be the alternative hypothesis. Either p is greater than 0.35, p is less than 0.35, or p is not equal to 0.35. All right. Now, when these hypotheses are written, the null hypothesis will have a number next to the equal sign. It could be a mean, or it could be a proportion. That number must match the number shown in the alternative hypothesis. Can't be a different number. It has to be the same number. So 5 is here. 5 has to be in one of these three. Same thing here. The proportion is 0.35 for the null. 0.35 is one of these three that's chosen as the alternative hypothesis. They have to match. All right, so that's important. Dr. Williams did not mention that. Now, she did mention that when we do hypothesis testing, she used the example of criminal trial. We assume that the null hypothesis H naught is true. All right, it's the standard knowledge about something, whatever we're measuring. All right, something quantitative in nature. We're assuming the null hypothesis is true to begin with. And then we take our sample data, and we want to see if the sample data that it provides enough evidence. In this case, we would call it enough statistical evidence to say that the null hypothesis is highly unlikely, and therefore we're going to reject it in favor of the alternative hypothesis. So we would say accept or the alternative hypothesis. So if there is enough evidence, we state that the alternative hypothesis is statistically significant. That's another term for accepting the alternative hypothesis, is that if there is enough evidence and we reject the null hypothesis, we will be basically saying that the alternative hypothesis is statistically significant, meaning that there's enough evidence to say that is the competing hypothesis is probably correct. Now, if there's not enough evidence statistically, then we do not reject the null hypothesis. This is not the same thing, and so we do not accept the null hypothesis, all right? We do not accept the null hypothesis as true, since it can still be false. All right, now what does that mean? Now, when I say we do not accept the null hypothesis, it means we don't use the word accept, all right? In other words, if there's not enough evidence, we would say we do not reject the null hypothesis, okay? We do not say we accept the null hypothesis is true. Now, what do we mean? Well, let's think about a criminal trial. Somebody let's say the person committed a crime, whatever the crime might be. However, the district attorney, you probably watch television, the district attorney didn't have a good enough case, didn't have enough evidence to convict that person. So the jury basically said, not enough evidence, we're going to let the person go. So what has happened? Well, there's not enough evidence to reject the null hypothesis. So what happens? The person goes free, right? The null hypothesis, the person is not guilty, and we didn't have enough evidence to reject that hypothesis. The person goes free. But it does not mean that person was not guilty. It doesn't mean that. It just means there wasn't enough evidence to convict a person. It's still possible that person committed the crime. In the same way, we don't have enough evidence from our data to reject the null hypothesis, we don't say, well, we're going to accept the null hypothesis as true. No, we just didn't have enough evidence to reject it. So we say we do not reject the null hypothesis. We do not accept the null hypothesis as true, okay, since it can be still false, despite a lack of evidence in the data. All right, so I hope you understand what I mean by that we don't make the statement something like, all right, not enough evidence to reject the null hypothesis, therefore I'm going to accept the null hypothesis true. No, we can't say that, right? It's still possible the null hypothesis is false. So what do we say? We don't reject the null hypothesis due to lack of evidence. That's what we say. All right, hopefully that's somewhat clear to you. Again, these sort of things I will repeat over and over again. We do actual examples, so don't worry about it. Now, this chart here is a typical chart that's shown in most statistics books that looks at a comparison of two things. On the left here, we do our statistical test. Now, for those of you who are in the Camden County course, the traditional statistics course, this will be an actual formula that we'll be using to do this test. For those of you at Rowan University in the statistical literacy course, we'll be using StatKey instead. But regardless of what we're using, we're going to have a test and we're going to see the result of the test from the sample data, all right, regardless. And there's either two decisions from that test. Either we're going to reject the null hypothesis, all right, and there's enough evidence to reject the null hypothesis, and therefore we'll accept the alternative hypothesis. Or, and that's called significant result, or there's not enough significance, not enough evidence to reject the null, and that's that decision. So we either reject the null or we don't reject the null. Those are the two decisions. Now you have to remember we have sample data. Sample is a subset, a small subset of the entire population. And typically when we do hypothesis testing, we really don't know anything about the population parameter in general. We don't know what the true value is, otherwise we wouldn't bother with the test. So in reality, it's an unknown reality of the actual population parameter that we're testing. It's unknown. So in reality, either the null hypothesis is true or the null hypothesis is false, and the alternative is true. So, but that's unknown. It's unknown. So I hope you understand these two different things here in this chart. Along the left here is the result of the statistical test. We're either going to reject the null hypothesis from the data or we're not going to reject the null hypothesis. Up here, along these columns here, is the actual unknown reality. In reality, either the null hypothesis is true or it's not true. Simple as that. Now, Dr. Williams mentioned two types of errors that are possible in a hypothesis test. The first one is called a type 1 error. It's in this box here. See, there's 4 boxes. This box here is an intersection of this row, where we're rejecting the null hypothesis, and this column, where we are stating that in reality, the null hypothesis is true. So this is an error, right? If our test says there's enough evidence to reject the null hypothesis, and yet in reality, the null hypothesis is true, that's an error. And that's what she called a type 1 error. Now, if you reject the null hypothesis and the null hypothesis is false, well, you made a correct decision, didn't you? Now, you don't know that, obviously, since the reality is unknown. But if you happen to reject the null hypothesis and the null hypothesis is false, that means that the test that you did is correct. It was a correct decision. Now, suppose that there was not enough evidence to reject the null. Okay. And suppose the null hypothesis is true. So that's this box here, the intersection of this column, that the null hypothesis is true, and that we don't reject it. So if we don't reject the null hypothesis, and it's actually true, that's also a correct decision. Okay. However, if we do not reject the null hypothesis, and the null hypothesis is actually false, then that is also an error. That's this box here, the intersection of this row and this column. And that's what she called a type 2 error. So let me review the type 1 error again. The type 1 error is when we reject the null hypothesis, when the null hypothesis in reality is true. And a type 2 error is the case where we don't reject a null hypothesis, but the null hypothesis is actually false. We should have rejected it, but we didn't. All right. So those are the two types of errors. The other two decisions are correct decisions. Now, she used the courtroom analogy. So if the null hypothesis is that the person, if the null hypothesis is true, that means the person did not commit the crime. All right. But suppose they get convicted. In other words, the jury rejects the idea that they're innocent and says there's enough evidence to show that the person committed the crime beyond a reasonable doubt. Then we've created this error. We reject the null hypothesis, which means we're going to send the person to jail, when in reality the person's innocent. So that's a type 1 error. Using the same courtroom analogy, if H naught is false, now remember H naught, the null hypothesis is the person is innocent. So suppose H naught is false, which means the person committed the crime, but there's not enough evidence to convict, right? Which is this here, we do not reject the null, then we've committed this type 2 error. And in this case, what happens? The person doesn't go to jail when they should have gone to jail because they committed the crime. In other words, a guilty person has been let free to maybe commit another crime in society. In my view, probably as far as society is concerned, a type 2 error is worse, right? Because you're letting a criminal back into society. As far as the criminal, the person himself is or herself is concerned, type 1 error is the worst thing, because if the person's actually true and got convicted, that means you're going to jail for a crime that they didn't commit. All right. Now, Dr. Williams also mentioned this idea of alpha, the probability of a type 1 error. So the probability that you committed a type 1 error, that is, you reject the null hypothesis when the null hypothesis is actually true, it's called alpha. We use the Greek letter alpha to represent this probability of a type 1 error. The other type of error she mentioned, the probability of a type 2 error, where we do not reject the null hypothesis when the null hypothesis is actually false, that's called beta. All right, so the beta is the probability of a type 2 error, alpha is the probability of a type 1 error. By the way, just for your own information, there's also a term called the power of the test. Now, a researcher, they're always trying to reject the null hypothesis because they have a different view than the standard view of the world. Right? That's why they're doing the research. They believe there's an alternative explanation for something. So their job, their goal, hopefully, without any sort of manipulation, is to reject the null hypothesis when the null hypothesis is actually false, right? That's a correct decision. This one up here. They want to reject the null hypothesis, that's their goal, and they're hoping the null hypothesis is actually false. And that probability is called the power of the test, all right? The power of the test is the probability that we reject the null when it's actually false, that particular correct decision. Now, this is an advanced topic, which for those of you in the statistical literacy course, I won't go into any further. Just know that that's the definition of it. For those of you in the Camden County course, I will go into it a little further with you guys, all right? Because it's more of an advanced topic. All right. Now, the alpha, that's the probability of a type 1 error, is also called the level of significance. The level of significance. Now, why do we call it that? Because that's the amount of type 1 error that we can, as a researcher, tolerate. I think Dr. Williams mentioned that, right? If you pick 0.05, you pick some small number, like 0.05, which is a 5% level of significance. We're basically saying that when we reject the null hypothesis, we can live with up to a 5% alpha error, type 1 error, because 5% is okay. We can't get it to 0%, but 5% is okay. And we know that in 95% of the time, we'll get it right, all right, when we reject the null hypothesis. In other words, the power of the test will be good. Now, so what happens in reality is a researcher is going to determine this alpha up front before they do the research. Now, typically in different fields of study, there's a standard alpha that's picked by researchers in that field. Many fields pick 0.05 or a 5% level of significance, but there could be some fields, in the sciences especially, where you pick a 1% level of significance. But you do this before you begin your research. That's typically when you do it. So what Dr. Williams was about to show you using formulas was this following idea. The idea is that by using alpha in a particular way, and again, I will show this to you guys next week, and either through StatKey or through formulas, you're going to use alpha. And what you're going to do is that by using this alpha, this level of significance, we can determine if the sample value that we get from the sample, right, the sample value from the variable of measurement, or if it's the proportions, the sample proportion, what we're going to determine is this value that we come up with from the sample sufficiently far away from the hypothesized value of the null hypothesis to make it unlikely that the null hypothesis value is true. In other words, for example, like the example we had before, let's just go back in the previous page. Suppose the null hypothesis is that the population mean is equal to 5. Suppose we get from our sample data, a sample mean of 7. Right? Now we know 7 is bigger than 5, but the question is it significantly bigger than 5, so that it's highly unlikely that if the true mean is 5, we would have gotten a sample mean of 7. Okay, that's really what we're asking. If the true mean is really 5, okay, but we got a value of 7 in our sample as the mean, is 7 so much bigger than 5 that we think it's highly unlikely that we would have gotten a 7 in our sample when the true population mean is 5. Remember, a sample is just a subset of a population. So if the sample mean is, population mean is 5, which we don't know, but we're guessing that's what it is, okay? But we get a sample mean of 7, we have to start thinking, is 7 so much bigger than 5 that we think it's highly unlikely that the true population mean is 5. If we come to that conclusion through the methods that I will show you, then we will reject the null hypothesis and say, we think there's enough evidence through the sample mean of 7 to conclude that the population mean must be greater than 5. All right, I hope you get the idea there. So is the sample statistic that we calculate, the mean or the proportion, sufficiently far away from the population mean that we decide that this can't be sampling variability from the population mean? It must mean that the true population mean is something different than 5, in this case, greater than 5. All right. So this will become clear when we actually do some examples. All right. So that's the key. Is it sufficiently far away? If this is the sample statistic sufficiently far away from the population parameter that we can justify rejecting the null hypothesis and saying the alternative hypothesis is true. Now, there are three, as Dr. Williams showed, there's three types of hypothesis tests. There is, now there's the three types are called the two-tailed test. Now she called what I call the left tail test, the lower tail test, but just to me, it means the same thing. I'm just referring to the left tail, as she's calling it the lower tail, it means the same thing. And the other type of test is the right tail test, which she called the upper tail test, which is the tail on the right. So what does this mean? What does it mean? Well, whatever problem we're going to be working on in hypothesis tests, whatever problem we're going to be working on, we're going to have a pair of hypotheses from the way the problem is written up. The problem in the wording of the problem will determine the null and alternative hypothesis. Again, you'll see examples of this next week, okay? Beginning next week. So, for example, let's say mu is equal, the population mean is equal to 10 is our null hypothesis, and that the alternative hypothesis is mu is not equal to 10. That is, it's either lower than 10 or bigger than 10. Suppose we pick alpha equal to 0.05. Alpha is 0.05. That's our level of significance. We determine that up front, right? We want to pick that as the probability of our type 1 error. We're tolerating 5% of the times when we reject the null hypothesis. We're okay with it, the fact that 5% of the time when we reject the null hypothesis, that we're making a mistake, that the null hypothesis is actually true. So how do we actually do this? Well, we have our bell-shaped curve, right? Bell-shaped curve, and for those of you in the course, the statistical literacy course, when we create our randomization test, we'll create something that looks like a bell-shaped curve, just like we did with hypothesis tests. So for a two-tailed test, if the alternative hypothesis is saying that mu is not equal to 10, and we're using alpha as 0.05, what we're doing basically with the two-tailed test is we're going to take our alpha of 0.05, which is 5%, and we're going to split it into two. We're going to divide it into two equal pieces. Half of the 5% is going to go to the left tail, and half of the 5% is going to go to the right tail. I'm just coloring in those two tails there. And half of 5% is 2.5% in each tail. Now, we're going to call this region in here and this region over here the rejection regions. And the region in the middle between these two values here, between these two vertical lines here, we're going to call that the non-rejection region. So what does that mean? Well, the mean, the hypothesized mean is 10. So that's going to be in the middle. That's going to be our hypothesized mean in the middle. What we're saying basically is, if the sample statistic, suppose the sample statistic is 15. I'm just making that up, right? Positive 15. And suppose 15 is somewhere along this line. It's bigger than 10, but it's to the right of this vertical line here. It's somewhere over here. The value of x, this is x here, what we're measuring, is in this region here, right? Here's the deal. If the value of x is in this region here, where we're shading the tail here, in this so-called rejection region, that means we're going to reject the null hypothesis, and we're going to accept the alternative hypothesis. In other words, the value of 15 is sufficiently away from 10, where it's in this so-called rejection region. Alternatively, let's say somebody else does a sample, and you find that your sample mean is 5 instead of 15. Suppose 5 is inside this region here, all right, inside this region. This is also a rejection region for a two-tailed test. Now, how do I know it's a two-tailed test? Because mu is not equal to 10, all right? The alternative hypothesis is saying mu is not equal to 10. It's either less than 10 or greater than 10. That's what not equal means. So if your sample statistics in this region Say, suppose 5 is in this region, we also are going to reject the null hypothesis and state the alternative hypothesis that mu is not equal to 10 to be true. Suppose somebody else says, oh, I'm getting a sample statistic of 11, positive 11. And suppose 11's in this white area here, this non-shaded area. Well, this is the non-rejection region. So if the 11 is in this region, we do not reject the null hypothesis. We state that there's not enough evidence to reject the null hypothesis. Or another way of saying it is, 11 is not as far away as 15, and it's in this region here. So we say that, hey, you know what? This is just normal variation around the true population mean. It seems pretty normal that you can get an 11 for a samples mean when the population mean is 10. It's in this region here. Or maybe somebody else gets a 9 or an 8 for a sample mean, and it's in this region, this white region here. So this entire region between these two vertical lines is the non-rejection region. You get a sample statistic that's inside this interval here. We're going to not reject the null hypothesis. There is not enough evidence to conclude that the sample statistic, the sample mean, is sufficiently far away from the population mean. All right? And if it's not sufficiently far away, we do not reject the null hypothesis. Again, this will become clear later. But the wording of the problem that we're looking at, whatever the problem is, will determine the alternative hypothesis. The alternative hypothesis is going to determine which of these three tests we're going to use. So if there's a not equal sign as the alternative hypothesis, we're going to use this two-tailed test. Now suppose the wording of the problem we're looking at, and we're going to use a proportion in this case here. Suppose the wording of the problem indicates that the alternative hypothesis, the competing hypothesis, is that the population proportion is less than 0.45. The null hypothesis is that it's equal to 0.45, but the alternative is that it's less than. Suppose in this case our type 1 error, probability of a type 1 error, or our level of significance is 0.01 or 1%. Now, this is called a lower tail test or a left tail test. I like the term left tail because it makes it clear which direction you're looking at. And since it's a one-tail test as opposed to a two-tail test, we're going to actually color in here an area that's equal to 0.01. All right, this whole area here is 0.01 or 1%. So we only have one rejection region when we have a left or lower tail test. And we put the entire amount of the level of significance, we put the entire amount there. Now, if we get a sample and our sample proportion is much less than 0.45, let's say 0.35, and let's say 0.35 happens to be in this region here, this 1% rejection region, we're going to reject the null hypothesis and state that the alternative hypothesis that p is less than 0.45, the true population mean is less than 0.45, is probably true. However, if we get a sample proportion that is less than 0.45, but not significantly far away, for example, 0.40, let's say 0.40 is in this non-rejection region, this white region, then we would say there's not enough evidence to conclude that the population proportion of 0.45 is not true. Okay, there's not enough evidence to reject it, and therefore we're not going to reject the null hypothesis. Remember, it does not mean that we accept the null hypothesis as true. We just don't reject it because it's still possible that it's false. All right, so this is called the 99% non-rejection region, 1% rejection region. Alpha determines the rejection region. Then finally, let's look at a third example. This is the example of what's called a right tail test or an upper tail test. Let's do this as an example with a population mean of 100 as the null hypothesis. And let's just say that the alternative hypothesis is that the true population mean is actually greater than 100. In this case, we're going to use a larger alpha level of significance as 0.10. What do? Since it's a right tail test, an upper tail test, we're going to color in 10%, 0.1 as the region in the right tail here. That's our probability in here, 0.1. And then the rest of the curve to the left is the rest of the 90%. That's a non-rejection region. So once again, suppose we have a sample mean that is 120, for example, and suppose 120 falls into this rejection region here, we would say that there's enough evidence to reject the null hypothesis that mu is equal to 100. Okay? And that's because 120 is significantly bigger than 100. All right, based on the statistics that we use. All right, we haven't learned how to do that yet. But suppose that mu is actually 105, or excuse me, suppose the sample mean is 105 that we get from a sample. Suppose 105 is in the white region here, the non-rejection region. Then we would say, well, 105 is not sufficiently different than 100 or bigger than 100 to come to the conclusion of rejecting 100. In other words, 105 seems reasonable that 100, we could get a sample of 105 as the sample mean when the population mean is 100, just due to normal variation, normal variability. So the three types of tests are determined by the wording of the problem. Wording of the problem determines the null and alternative hypotheses. Now the null hypothesis always has an equal sign, and the number that we put next to it will be given in the problem. Always know that this number in the null hypothesis and the number in the alternative hypothesis has to match. If the problem states that the alternative hypothesis is not equal to, as opposed to greater than or less than, then this is called a two-tailed test. And we take our alpha, the level of significance, and divide it by 2 and put half of that area to the left tail, half of the area to the right tail. And then we color in these areas and call them rejection regions. And then the area in the middle is the non-rejection region. And then we take a look at our sample statistic to see if it's in one of these rejection regions, which means we'll reject the null hypothesis, or if it's in this non-rejection region, which means we will not reject the null hypothesis. If the reading of the problem says that we have a left tail test, that means there's a less than symbol in the alternative hypothesis. Then we do a left tail test or a lower tail test. We take our entire alpha that's stated in the problem and we put that whole entire area in the left tail. We make that the rejection region. It's only one rejection region. And we make the rest of the area underneath the bell-shaped curve to be non-rejection. So if the sample proportion in this case is significantly less than 0.45, to the point where it's in this region here, rejection region, we're going to reject the null hypothesis, saying that the true population proportion there's enough evidence to say that it's less than 0.45 and not 0.45. Because it's highly unlikely that you would get that sample statistic if 0.45 is actually true. And we have the right tail test. So the wording of the problem says that the alternative hypothesis is greater than, as opposed to less than, or not equal to. It's greater than. So we know because it's a greater than problem that we're going to use a right tail test. We take our level of significance and we put that entire area into the right tail. We make that the rejection region, and everything to the left of that will be the non-rejection region. Once again, if our sample mean is significantly bigger than 100 to the point where it's in this region, this rejection region, we're going to reject the null hypothesis, and we're going to go with the alternative hypothesis. If it's in this white region, where it's not as far away from 100, we're going to say there's not enough evidence to reject the null hypothesis because the sample mean is close enough to the population mean where it could be just normal variability. Well, that was a lot of words. I hope you understand somewhat what I've talked about, maybe 10, 20%, hopefully, of what I talked about. When we do examples, which we will be doing over the next couple meetings, basically for the students at Rowan, this is going to be the last topic that we'll be doing, the hypothesis test. So this will be for the remaining of the semester. We're going to be doing it using StatKey. So we're going to show you through examples, actually word problems, and we're going to use StatKey as a way of coming up with our decision whether to reject the null hypothesis or not. Okay. Those of you who are in my class at Camden County College, you'll see how to do it with formulas. Okay, so that'll be the technology that you'll be using. But regardless, it'll be starting next week. So please, hopefully you've seen this and you can see this many times, this particular review. So I'm going to stop sharing now. And so that's it for today. I hope this was useful as an introduction. A little bit probably tomorrow, I will, for the students at Rowan, I will list the, I'll probably post in Canvas the sections of your textbook that you can read that gives you additional background for all of this. For those of you who are in my course in Camden County College, chapters 10 and 11 will be the ones that we're going to be focusing on over the next couple sessions. Okay, and that is it for today. So thanks for listening. Have a very nice holiday. If you're listening after Thanksgiving, I hope you had a nice Thanksgiving. If you're listening before you have your dinner, enjoy your Thanksgiving dinner, and I will see you next week. Okay, so stop the recording now.